So we are going to go over lessons 7 through 10. That's going to be the lessons that are going to be on the midterm. Basically the second half of the semester that we've been doing. So we're briefly going to go over them, and I do have review session or review questions throughout that we will go over as we cover the topics. And so if you can definitely go ahead and participate in those will definitely support your review of these topics. And at the end, obviously we're open if you have any extra questions. And yeah, and obviously ask any clarifying questions throughout if you're confused about something or need to go more in depth. And also keep in mind that we do have the rest of the reviews that are specific to each lesson and are more in depth that we go through. So what I usually suggest as we go through these reviews is mark down things that you kind of forgot about maybe, or you're like, oh, I have to review this, so that you can go back to that later on, and then understand that that's something that you're going to want to review when you go back and study on your own. And like I said, you can go to the YouTube channel and check out the videos that we have specifically for each chapter that are a bit more in depth than the brief review we're going to do now. Okay, so these are the topics that we're going to go over. So basically, I kind of clumped 8 and 9 together when we do it, just because they're inferences and samples in general. But we will talk about one sample and then grow upon it with the 2 samples. But we are going to start with common distributions and end with one-way ANOVA, which we just did. So that'll probably be pretty fresh in your mind. That's a very short chapter too. So let's start with lesson 7, our common distributions. So basically, the one that we specifically talked about in depth was our binomial random variables. So these are a specific type of variable, and we are talking about quantitative variables for this. Remember, we have discrete and continuous when we're talking about quantitative variables. So that's something to keep in mind. You want to make sure you make that connection. And so basically, and so it's a discrete random variable, meaning that it can only take on a set number of values. And basically, the idea of binomial random variables is counting how often something occurs. And then this idea here, a fixed number of tries or trials, that's actually one of our conditions, but it is part of our definition of binomial random variables. And then in order for something to be a binomial random variable, we do have to have these 3 conditions that are met. So first, like I said, there has to be a fixed number of trials. So our n has to be something static. This has to equal something. It can't change when you continue on through your procedure. And then the second condition is the probability of a success is the same on each trial. We have to make sure that also, so this has a lot to do with consistency. So for this one, it's just saying, the probability of success is has to be a specific probability here. So this is going to be between 0 and 1 in decimals, and it has to be constant, obviously, and then trials have to be independent. So this is basically saying that they can't affect each other. So the whole idea here is that we want to have variables that are static and don't interact with each other in order to get the most accurate idea and the most accurate results here. All right, so we have our central limit theorem. This was basically something we talked about in terms, we had this and then rule of sample proportions, which we will go into. So these were kind of what we decided if we could use a variable to estimate our population. So in this case, for a central limit theorem, we do use our, this is for means. So remember, and rule of sample proportions obviously is going to be for proportions. So you can see mu here, this is going to be for means. And so yeah, we're asking, when can mu be estimated using a normal distribution? So remember, our sample is what we use to make an inference about our population. So remember, we have our population, and then we take a sample from it, and then from this sample, we're making an inference, excuse me, an inference about the population. So because it's hard to get, obviously, like information from the entire population, so that's why we try to take a representative sample, and if that sample is representative enough, we can make a, hopefully accurate inference about the population in general. So central limit theorem says, that our sample size has to be at least 30 in order for us to make this assumption. And then this does say regardless of the shape of the population, basically meaning that it could be skewed or it could be normal. It doesn't matter. In this case, it's basically saying if you have a large enough sample size, then you're able to make this assumption here. And so that means that your mean is going to be mu. So your sample mean, basically, we're able to attribute it to being our population mean. And then our standard deviation is going to be this equation here. And as you can see, we're using sigma, which is going to be the population standard deviation. That's the symbol we use for that. Remember, for our sample standard deviation, we would use the symbol of S. So that's just a review of that. Okay. And then this is basically just how we would actually compute the mean and standard deviation if we were given, values such as these. Basically, this is just algebra and basic math here. So an expected value is another way we can express the mean. That's why we have, e to the x, or excuse me, e x, and then which is equal to our mean, which is equal to our sample size times our probability, which, remember, these have to be the same across trials. Well, the probability has to be the same across trials, and then we have to have the fixed sample size. And this also has to be fixed sample size. So remember, these are just this has to do with our conditions of something being a binomial random variable. And so these are literally just equations, how to find them. So all you have to do is plug in whatever you have. And so remember, our mean is going to be our center here. And then our standard deviation is going to be our spread. So that's where this comes from there. So that's just, doing basic math here. So let's do a quick review question for this. So go ahead and look at this. And so I'm giving you a binomial random variable. So this is assuming that, all the three conditions are met. And we have n equals 15 and mu equals 8. So go ahead and try to compute the probability of successes and the standard deviation here. So try to calculate this one and type your answer into the chat box, and then we will review it. If you don't know it, just say I don't know, and we'll review it anyway, and let me know what you guys get then. All right, let's try going over this one if you guys are having some trouble with it. So if we check out here, we have, so our n is 15 and our mu is 8. So if we're trying to find our probability, we can use the equation of mu equals np, because we have everything of this equation except for the p, which is what we're trying to find is our probability. So all we have to do here is plug in our mu, which is 8 equals 15p. And then all you have to do is solve this equation out in order to find p. And then you find that your probability is going to be equal to 0.53. So that's how you solve for the probability. And then our standard deviation, remember our equation for our standard deviation, since we already found our probability, we're able to find this. So our equation for our standard deviation is going to be np, and then times 1 minus p. So all we have to do here is solve this out. So we have our square root of n, which is 15, times p, which we found in the first equation, so 0.53. And then we go ahead and then multiply this all by 1 minus p, which is 1.5 or 0.53. And then if you were to solve out this entire equation, you're going to get about 1.93 here as your standard deviation. So that's how we solve that. Basically, you have to use these equations and use the equations where you have all the information except for, one piece, so that you're able to solve it for that one piece there in that case. Does that make sense to everyone, how we came to that conclusion? All right, cool. Yay. All right, good job, guys. All right, let's continue on. So 8 and 9, like I said, I kind of put them together just because they're both talking about samples and inferences for samples, but we're talking about 1 and 2 samples. So just as a review, when we have data from 2 groups, we want to talk about if they're related to one another, what is the relationship to one another. So if they are independent, that means they're unrelated, they don't affect each other, basically everything about them is separate. In comparison to dependent or paired, it's another way to say it. That means that they're matched to one another, they're dependent on one another. If something happens to one group, it affects the other group in that case. So these are just 2 different types that you want to keep in mind to make sure you understand, when we're labeling these. So just to review that in general, just like that concept I just want to do this quick review. So our research question is, in fraternal twins where one baby is male and one baby is female, do the brothers tend to weigh more than the sisters at birth? So a random sample of 30 pairs of twins is obtained. Each baby is weighed for each set of babies. The weight of the female is subtracted from the weight of the male. So are these data independent or paired? So let me know which one, independent or paired, you think it is, and then we will discuss it. Okay, so we have mixed conclusions here. So let's read through these. So we're talking about fraternal twins. We have a male and a female. And then what we want to look at here is our design. So in our design, basically, you see when they're weighing them, they take the weight of the male and then, or the female, subtracted from the weight of the male. So that means that the weight, the data is going to change dependent on each part. So the difference in the weight, starting with the male, is going to change dependent on what the weight of the female is. So that means that they're going to be paired because they are dependent on one another. If one changes, the other one will change because we are subtracting them from one another. So that means that they are going to be related in that case. What happens to one will affect the other one in the final answer that you get there. So does that make sense why this would be paired then? I know this one's a little tricky, you know, because in general, if you think, you know, there's like males and females, you know, they're not related, but in the design is what our specific, you know, that's where it tells you about them. Yeah, so you want to make sure you're looking at the design and think about it. You know, if you all you want to think is like, if you change something in one group, is that going to affect the other one? And if the answer is no, then that means they're independent. If it's yes, then they're paired. So in this case, if you you know, you choose another female, you know, and the weight of the female changes, that is going to affect the male, and then the final answer that you get there. So they are paired. So good job. Hopefully that's clearer for you guys. All right, so remember we talked about our central limit theorem, but basically now we're going to talk about our rule of sample proportions, which is the same idea in terms of, you know, when can we use our sample in order to estimate a population. So basically in this idea, so our sampling distribution for P be estimated using a normal distribution. And this is just, so the conditions that have to be met for our rule of sample proportions, similar to our central limit theorem, is that we do have to have n times p be at least 10, and then n times 1 minus p be at least 10. These are, they translate into like successes and failures. You'll also see that. And basically it's saying that if these conditions are met, we're able to make this assumption here that our, the mean of our sample, so our mean of our p hat is going to be equal to our population. Sorry, the proportion, like technically, you know, our center proportion is equal to our average proportion in the population. So same idea here. We're able to use these equations for the mean and standard deviation for populations if these conditions are met. So that's just saying that's a rule of sample proportion, saying if these conditions are met, we can make these assumptions in these two equations here. Okay, so I'm not going to go like too far in depth about like all the different, like the last three steps, as we often talk about, are the same basically for every hypothesis test. You know, you find your p-value based upon your test statistic, make a conclusion based upon that p-value in terms of your null and alternative hypotheses, and then state your real-world conclusion. So basically, going through these hypothesis tests, we're basically just going to go over the first two steps for each of them, because those are the ones that are different depending on which hypothesis test you're doing and what types of samples that you have, and if it's mean proportion, so on and so forth. So our first one, so hypothesis testing for a mean, basically this is just saying, you know, we're trying to make a decision about a mean, a single mean here. We also call this a one sample mean t-test, because remember, for means we use a t-score, and proportions we use a z-score. So we have our hypothesis testing for a mean here, and basically the first step, remember, you have to make sure that you check the necessary assumptions, and in order to do this, so and remember, our assumptions, we have to have a big enough sample size, we have to have quantitative data because we're talking about means, and then they do have to be randomly sampled in order to have that representative sample there. So that's basically what needs to be, that needs to be met in order for us to keep going. And then our, this is just a table that we use about, you know, that shows our null and alternative hypotheses, and, you know, how you would write them in terms of your research questions. This is just a good reference, you know, if you're confused about how you should write your null and alternative hypotheses, to go check this out, and this will kind of give you a better outlook on it. So remember, this is going to be for one sample mean. And then for hypothesis testing for a mean, our test statistic, our second step is, this is the equation you use to find your test statistic for, once again, we're still talking about one sample. And this is just the equation. Our denominator is our standard error of the sample. And obviously you're given the key of the different, what all these symbols mean here. So this is pretty self-explanatory. It's just the equation that you find on that test statistic, which, remember, for a mean, we do use the test statistic of t. So we just talked about one sample means. Now we're going to talk about two sample means. You know, so paired means. Remember, paired means that they are dependent on each other. So if one changes, the other one will too. So our conditions that have to be met for hypothesis testing for paired means is that we do have to make sure that the data are paired, And then the difference between the groups has to be normally distributed in order, excuse me, in order to continue on with this hypothesis test. And remember, if it's not normally distributed and our sample size is at least 30, then we can also continue with it. The main idea here is that we want to make sure that we have a large enough sample size, or we understand that our population is approximately normal, so that we can go forward with this and make these assumptions in terms of our central limit theorem. And then once again, we just have our table down here of the different ways that you write your own alternative hypotheses, and if it's two-tailed, one-tailed, etc., based upon your research question here, just as a reference there. And then for paired means, and keep in mind that this looks very similar to the finding a test statistic for our one sample mean, but here keep in mind we have this subscript of D, which is showing that we do have that difference. So in that last problem that we did, this would be kind of like the difference in means of between the female and male babies. So you're looking for that difference because they are dependent on one another. So when one changes, the other one changes, because when they're paired, you're trying to find a common difference between them that you're going to use as your values here. You're not going to use both of them in the equation. You're going to use whatever you get out of the difference between both of them in the equation. So this is our test statistics, still talking about T because we're talking about means. And yeah, so that's our second step. Okay, and then moving on to proportions. So proportions are going to be when we're talking about you want to make sure you have the minimum of 10 successes and 10 failures. And like I said, this is, remember, we have to have our NP be at least 10, and then our N times 1 minus P, so this is our failures then, be at least 10 as well. And those are the conditions that have to be met here in this case. And then once again, so we're talking about two independent proportions, so these ones do not affect each other. And here you can see, we have our, technically, this is P1. Looks a little weird here, but they are subscripts. Another way you can write these two is you can have P1 equals P2, because in reality, if P1 and P2 are the same, and you subtract them, it's going to equal 0. So that's, you might see it written like that too. It's a different way. So this is just for two independent proportions. You have two different groups, which is where all of these come from. And then our second step for two independent proportions is we want to make sure we calculate that test statistic, which, remember, in this case we are talking about a Z test statistic because we're talking about proportions. And all you do here is basically so you have your Z is going to be whatever the that's going to be your test statistic that you end up getting, and then here you have your difference between the independent proportions, your null, and then your standard error of the null. So that's pretty self-explanatory. Okay, yeah. And then this is going to be for two independent means. So earlier we talked about just one mean in general, but here, as you can see, we have two groups. So we have the mean of group 1 and the mean of group 2. So the assumptions for hypothesis testing for two independent means is that we do have to have data that are independent. They're not paired, because remember, if they're paired, they are dependent on one another. And we do have to either have normally distributed populations for both groups, or we do have to have sample sizes greater than 30 in order to continue on with this hypothesis test and have that condition met there. And then once again, we are using T because we're talking about means, and then this is the equation that we use to find the test statistic for independent means. So here you have the two sample groups, or two sample means here for the it's for group 1 and group 2, and then our standard error on the denominator. See, we have to have both the standard error of our group 1 and group 2, and then takes the square root of that because we do have two independent means in this case. All right, so let's try a review question. So based on the 2000 census, 31.8% of Penn State students have visited the creamery at least 5 times in the past year. Suppose that our sample size is 200 people, and they're to be sampled from this population, and the sample proportion of students who visited the creamery at least 5 times, which is our p hat, our sample proportion, is to be calculated. So what is a standard error of the sample proportion? And remember to apply that rule of sample proportion. So this is just kind of making sure that you conceptually understand how to find this and how to find the standard error for this sample proportion. So go ahead and try this out and let me know which answer you think it is, and then definitely, if you're struggling and you don't know, just let me know that too, and we will go over it then. Yay, good job. Yeah, definitely. Our answer is A. So let's go over this. So what I like to do always, in statistics, as I'm sure you've noticed, you often get a big, paragraph of all this information. So what I like to do is just go ahead and pull out the different values that we get so that I can use them later in my equation. So here, as you can see, we have our proportion is going to be this 31.8% of Penn State students. That's our proportion of the students. So if we translate that to a decimal, we just get 0.318. And then we also have our sample size that's given to us of 200. And so after we get all this information, basically we can take this and plug it into our equation that finds our standard error of the sample proportion. So remember, standard error is the same thing as our standard deviation. So basically all you have to do here is take the square root of p times 1 minus p, and then divide it by n. And then if we were to translate this into this problem specifically, we would get 0.318 times 1 minus 0.318. And then we divide that by our n, which per the what we wrote down here, we have being 200. And then after we solve this, we're going to end up getting letter A here. So great job. Definitely understand that concept there. All right. So a few more review questions, because I know this is kind of a tricky subject for some people. So here we have, under old management, historical data show that 2% of customers felt that they received poor service at a restaurant. New management has taken over, and the manager wants to see if improvements have been made. You're asked to analyze data from a random sample of 100 common cards to see if less than 2% of the customers state that they received poor service during their visit. So this is conceptual, just kind of just, making sure that you understand how you can decide what type of procedure you're going to use. So go ahead and look through these procedures, and based upon this question, let me know which one you think it is that we would use here. Okay, good job, guys. Yeah, so let's look at this. So if we break it apart, remember if, so this is going to be a categorical variable because it's talking about if they received like good service or not. So this is going to be, a yes/no question, which is going to make it a categorical variable. So that means that we can basically knock out everything that says means because remember that's quantitative. So now we're down to all the ones that say proportions. And if we look at this, we're trying to decide, do we have, how many proportions do we have that we're looking at? And in this case, we really only have one proportion because you're talking about to see, if less than 2% of the customers, as you can see in the problem, we don't have any other proportion to compare with. So that means that we wouldn't have two independent proportions. And then in this case, so remember, our normal approximation method can be used if our conditions are met. So if our NP is at least 10, our sample size times our probability, or excuse me, times our proportion, and then our failures n times 1 minus p also has to be at least 10. So if we end up doing that, like checking for this, our NP is going to end up being 100 times 2%, which we're going to end up getting 2. And then 2 is, not going to be at least 10. So since it's not, that means that we can't use this normal approximation method because we can't assume that it's going to be normally approximated since our condition is not met here. So that means we have to use our exact method, which basically you can use the exact method no matter what, if your conditions are met or not, if you have skewed data or not. So we are talking about one sample proportion because we only have one sample here in the question, and then exact method because our condition was not met. So that's why we're going to have our exact method. Does that make sense to everyone? Woohoo! All right. Let's see. I feel like we have another one to practice. Okay, yeah. So because this is important, so that like obviously everyone can kind of plug and chug and do the equations, but it is important to understand what our what procedures we would use and why. So here's another one. So we have our research question. So do students score higher on the midterm exam or the final exam? So data were collected from a random sample of 30 students. Each student's midterm exam score and final exam score was recorded. So which of the following tests should be performed to address this research question? So go ahead, read through these and let me know which one you think, and we will go over it. All right, awesome. So let's look at this one. So we're talking about exam scores, which this is going to be a quantitative variable. And since it's quantitative, that means, remember, we're going to be talking about means. So we can take out everything that is proportions here. And so now we're going to be talking about means since we're talking about quantitative, like I said. And we want to discuss then how many do we have? Do we have 1 or 2? And in this case, we're comparing our midterm to our final. So that means we're going to have 2 groups. And in that case, that's why we have to make sure so we can knock out this one sample means t-test because we're going to have 2 different means here. And basically the last decision we have to make is it going to be paired or independent? So idea here, remember, you want to discuss if one of these changes, will the other one change as well? And as you can see in our research question, they're trying to decide that if students score higher, you know, which one do they score higher on, and they're recording both of them. And since they're both, remember, paired samples are usually taken from the same group. So in this case, you know, you have your group of students, you know, with their midterm, and then for the same group of students, you're going to have their final taken. So these are all going to be the same student and their same grade. So, you know, what they get on the midterm is going to affect the difference, you know, that that happens on the final. You know, the difference here is going to be affected dependent on, you know, what value you get over here. So that means we're going to have a two-paired means t-test here, because we do have these means being dependent on each other, because as one changes, the other one can also change there. They aren't independent of each other. That would mean that they have no effect on one another. So that's going to be two-paired means t-test. Does that make sense? Yes, yeah, okay, yeah, that's a good point. So think of it in this way. So remember, when we have the paired means t-test, remember how we have that subscript D, because we're looking at the difference. So it's saying that if you have your midterm grade, and let's say your midterm's a 50, and then your final is a 60, then your difference is going to be 10. But if your midterm is 50 and then your final is actually 70, then they're going to be dependent on one another, because that difference is going to change there. Then it would be 20. So that's why we would end up, because they are dependent on one another. If one of them changes, when we're talking about two different means, then the other one's also going to change them, or then the difference is going to change. And so you're trying to see that relationship there. Does that make sense? Okay, awesome. Good question, though. Definitely thinking that's a great question. Okay, so here's another one. So is the proportion of girls who like strawberry ice cream different than the proportion of boys who like strawberry ice cream? In a sample of 40 girls, 27 like strawberry ice cream, and then in a sample of 45 boys, 25 of them liked it. So which graph, this is like a two-part question. So which graph would you use to display these, and then what test would you use to address the research question? So try this one out, and then we will review it. Okay, yay. So let's look at this one. So for our first question to address this, we have to understand basically, are we having quantitative or categorical data here? So in this case, it's basically saying like yes or no, do they like strawberry ice cream? So do they like it? or not like it. So in this case, that makes this a categorical variable. And then since it's categorical, that means that we are going to have to use a display that shows categorical data. So B and C are out because these are both ones that we use for quantitative. And then that's supposed to say quantitative. And then so A would have to be our answer because we're talking about a bar chart, or we're talking about categorical data, so that's going to be a bar chart there. And then for our second one, we're trying to decide, and this, like how many, so we have to talk about first, are we talking about means or proportions? So since we're talking about categorical, that means that we are going to be talking about proportions. So we can cancel out the ones that are means. And then we want to decide, are we talking, and then, so our two options are either having two independent proportions or having that one sample. In this case, you can see that we have a sample of like how many girls and then a sample of boys. So that means that we're going to have two proportions there. So our answer is going to be, have to be this two independent proportion z-test. And remember, you know, with our proportions, we use a z-test, and then for means, we use t. So yeah, that's our answer there for that one. All right, good job. All right, just a little bit more for our last one, talking about one-way ANOVA. So we did just do this one, so hopefully this is pretty fresh in your mind. So remember the idea, you know, that the reason why we don't just take a bunch of t-tests for an ANOVA like procedure is that you would have to do a lot of tests in order to continue, in order to like get the results that you want. And then by taking all of those tests, remember we always have that alpha level, which is our chance of having a type 1 error. And the more tests that you take, it's going to increase that chance of getting it. And it says could inflate alpha. It's the same idea there, that alpha is, you know, our chance of getting a type 1 error, which remember is our incorrect rejection of a true null hypothesis. So a false positive when we are rejecting that null when it was actually true. So we said that there was a change when there was no change. And then, you know, if we did all this, we wouldn't really have information about that independent variable overall. It would just kind of have, like, based upon all these samples that we're taking. So that's why, you know, taking a bunch of t-tests wouldn't really be something useful, and that's why we use ANOVA instead. So once again, you know, for hypothesis testing, we're going to go over those first two, the first two steps, because those are the most common ones that we, or the ones that change dependent on what which like test we're doing, which procedure. So for ANOVA, our first step to check our assumptions and write that null and alternative is that our assumptions have to be that we have each sample being independent random, our distribution has to be normal, and then the population variances have to be equal. And the main idea for it, so the definition of like three, the third one, you know, it's a little, you know, you have to understand conceptually what it is. So, you know, that just means basically that our null hypothesis is that all of the groups of the population means are equal in this case, so that in that case we're saying that we want those variances to be equal as well for those assumptions to be met. And now remember, we always assume that the null is true. So, you know, here we have that our each mean of each group is going to be equal to one another. And then our alternative is saying that at least one of the means are different. You know, it could be one or more, but if at least one of them are different, that's our alternative hypothesis. And our F value, this is a different test statistic that we, instead of the ones that we've been using. So remember, for proportions, we've been using Z, means we've been using T. So for ANOVA, we end up using F, which you get out of a Minitab output, and then your p-value will be based upon that there, and then you finish out with those last three steps of a hypothesis test. So let's try this one review question for ANOVA. So a study compared testosterone levels among athletes in 4 sports: soccer, track, lacrosse, and water polo. The total sample size was 30, so 10 soccer, 10 track, 5 lacrosse, 5 water polo. A one-way analysis of variance was used to compare the population mean levels for the 4 sports. So for our F test, remember, for ANOVA, we do use the F test. Our P was 0.02. So using an alpha level, so our probability of a type 1 error as 0.05, 5%, what is the conclusion that we would make? So basically this is like our third step there of our, well, technically our third step of, no, sorry, our fourth step of the hypothesis testing procedure. So we found our p-value, and make a decision here on what you think the conclusion that we would make is. Okay, good. Yeah, absolutely. So our answer here is going to be B. So as you can see, our p-value, remember, for p-value is less than our alpha, we are going to end up rejecting the null. So in this case, our p-value is 0.02, which is less than our alpha, which was 0.05. So we're able to reject the null hypothesis. So that means that we're basically between B and D, because C and A are talking about it not being rejected, which is not true. So, and then basically we kind of have to understand that if we reject that null hypothesis, what does that mean? And remember, we're always, we're making these inferences based upon what we got from the sample. We're making inferences about the population. So we'll make sure that our final conclusion is always discussing our population in general. So that's why our answer would be B, because we're not talking about our sample means. We're using the sample to make an inference about the population. So our final conclusion is going to be about our population there. So great job. All right, so that's all that we have for tonight. Thanks for sticking in. I know that's definitely midterm reviews are quite long, so our next group review is going to be on Thursday at 10 o'clock. If you want to stop back in, if you have more questions or want to review anything, like I said, if there's topics that you definitely, you wanted more review on, definitely go check out the more in-depth videos on the YouTube channel. And yeah, if you have any other questions for me, let me know. If not, you guys should be good to go for tonight.